that will be illustrated in this case here. There will be two-dimensional features here. In this case here, you have x1 and x2. You have two features here. And now you have, these are the training data sets you have. And then the ones represent the data is labeled with class label 1, and 0 means that there is a training data set here. Its class label is 0. And now we talk about a binary classification example in this case here, either 1 or 0. And you have 1, 2, 3, 4, 5, 6, 7, 8 training samples we have here. Okay, so now suppose you are presented with a new data sets here, located at this point here with this x1 and x2 here. And what is the class label should I assign to this new data sets here, right? So that's the classification problem. Well, in order to answer that question here, and if I use the nearest neighbor approaches here, so what I'm going to do here, and I'm going to look at look for which data point that is closest, that is its nearest neighbor to this one's here. And I find this is the nearest to this one's here because, and the distance between this is further away, this is further away. So this is the one here. And because this data set is annotated with label 1, so correspondingly, I'm going to predict that the labels of this data is going to be 1. And that's the nearest neighbor classification approaches of them. Right? So of course, when I do this type of exercise here, I need to have a metric of, to measure the distance between the two data points here, right? And for instance, there are many metrics we can use. And for instance, very commonly used metrics here for in the nearest neighbor approach here is based on Euclidean distances. And that would be simply measure calculate the norm or the Euclidean distance between these two data points of that. And that's something you are very familiar with. But by no means this is the only metric here. And there are many other metrics that can be used to measure the distance between 2 points. And it turns out, I think in the end, we'll come to revisit this concept again. So it turns out nearest neighbor approaches is very generic approaches here. What makes nearest neighbor approaches challenging is how to come up with the distance metric to measure the distance between two data points here. If you have a clever way to measure distance between two images, and then you can solve the classification problem easily. And however, in many cases, it turns out that to come up with the correct distance metric is fundamentally hard. And that's the reason that even though nearest neighbor approach is, it's a good idea, but in the end, you have to come up with distance metric. And that is not easy to come up with. However, for now, we're going to assume we're going to use Euclidean distance as a distance metric to measure distance between 2 points we have here. All right. So as a result of that, that will be this length of the connection between these two dots here. All right. So this is the decision boundary. We call decision boundary of this nearest neighbor approaches for this two-dimensional classification problem. If you apply nearest neighbor approaches to all the data points within this two-dimensional plane, and then in the end, you'll be able to assign class label to each one of the data points on this plane. And the result will look something like this. For all these regions here, you can assign those labels to be 0. For all regions here, in this pink regions here, you can assign labels to be 1. And you have a clear separation of the two regions here. And usually we call this type of things here, the boundary between these two label regions, we call it decision boundaries. And that terminology is very common, not only for nearest neighbor approaches, but for many, many machine learning approaches here. Sometimes we always think about what is the decision boundary for those for this particular approaches. Because fundamentally, what matters most are those data points here, because those data points sitting around here are those hardest, most difficult data points to make judgment, make decisions. Because for data points here, it's most times very easy to say, what this is label 0. For this data point here, this corner here is label 1. But what usually the hardest examples are those located within the boundaries here. And that's the decision boundary each model need to make here. And that one was made by the nearest neighbor approaches. What you can see from this decision boundary is this. It's very similar to the regression example I just showed you. You see the decision boundary here is piecewise constant, piecewise linear, or okay, we say it's piecewise linear. It's kind of a line here, but then you change these lines from one line slope to the other ones here. But however, you see the decision is not curved. It's a straight line, only kind of piecewise straight line here, but it's not a kind of smooth curve along the decision boundary of that, or it's not a straight lines of that. And that would be the result from other models. But for nearest neighbor approaches here, you will see it's kind of piecewise line, piecewise constant linear lines along the decision boundary. That's the very hallmark of nearest neighbor approaches there. So why is it kind of piecewise lines here? The reason is this, right? So similar to the regression models here, and essentially the decision boundaries here are those points that have equal distance to its two nearest points here. And now be along this decision, these vertical lines here. And because of the screen here, they are not exactly vertical, but it should be, this black line is exactly perpendicular to this dashed lines here. And then this point here is the middle point between 1 and 0. And then you can see that along these lines here, because it is perpendicular, it's equal distance to 1 and 0 to its two nearest neighbors of that. Essentially, along these lines here, it has two neighbors here, right? Because it has equal distance to the left neighbor and the right neighbors here. And as a result that its label assignment is unclear, which I should assign to. It can be 1, it can be 0. In fact, it's left undetermined along the decision boundary. You can assign any one of them randomly because it's very hard to change them. But as long as you switch slightly back to the left side here, you can assign everything to be 1 and right hand side to be everything to be 0. And that's the reason here, you will see this kind of piecewise constant function here. However, whenever you transition to this point here, now you encounter another neighbors here. So now along this line points here, you have equal distance to two different sets of neighbors here. Now this become closer than this ones here. So that's the reason you draw another decision boundary. So as a result, you can extend all the way throughout the entire graph of that. So you get this so-called piecewise linear boundary. That is a very unique features of nearest neighbor approaches. All right. So this is in the end, you have the concept came up around this concept of Verona diagrams of that. So Verona diagram going from the other way, essentially kind of grow its neighbors from each individual samples. You grow neighbors with equal distance. In the end, at some point, those neighbors is going to grow in bigger and bigger, will touch each other. And then whenever it touches, right? And that will be the decision boundary between those two data points here. And now it touches here, they have equal distance. And then in the end, you get this decision boundary. Now it becomes kind of piecewise constant, piecewise linear functions of that. Okay. So this is called a Verona diagram that is associated with the nearest neighbor approaches. All right, so when you have more data points here, so the data point that I have shown you here is kind of relatively smaller data sets here. But you have more data points here, your decision boundary become more and more complex. And then now there's, you can see more or less the decision boundary may look something like this. So in this case here, again, I have another one set of features here, and then another set of features here. Now I have data points here, and one is labeled with the 1. Another set of data is labeled with label 2 here. And then similar to the 0, 1, I just show you here. But now I just put up two different numbers here. So now if you try to draw the decision boundary, and now you can see your decision boundary become very complex now, right? Because convoluted. It's because you have because of these training samples here, you have to dig in and pull this out here in order to make the correct decision boundary. So you can see your decision boundary becomes more and more complex. And that's very common.